previous breakdown of the autonomous decision-making agent, we looked at a system optimized for the immediate present. Agent number 1 evaluates an environment, checks a safety limit, and executes a single response. It asks, "What do I do next?" This map shows the 30 specific architectures required for modern AI engineering. Right now, we are stepping up to level 2 of the foundational cognitive tier, the planning agent. The blueprint we are following hems directly from Imran Ahmad's foundational text, 30 agents every AI engineer must build. A purely reactive system has no temporal horizon. If you hand it a single customer service ticket, it succeeds. Ask it to coordinate a multi-stage product launch spanning 3 weeks, and it collapses. It lacks the ability to map out parallel dependencies. To manage a long-term objective and cross the gap into genuine autonomy, you must upgrade your system design. You have to move away from triggering isolated reactions and start orchestrating strategic, long-horizon logic. Imagine you task an AI with a high-stakes engineering objective, migrating a live production database with absolute zero downtime. A reactive script treats this job like a flat to-do list. It runs the first steps without issue. Then, an unexpected error blocks a mid-level transfer. The script can't navigate around it. That single failure shatters the sequence, taking down every scheduled task. In a live production environment, you cannot simply hit reset and run the entire migration sequence from scratch. This requires an entirely different class of system. You need an agent that holds the overarching goal in its memory, understands which tasks rely on others, and possesses the ability to surgically repair the broken branch while leaving the rest of the operation intact. The core thesis of the planning agent architecture is counterintuitive. Its true value does not lie in generating a perfect initial plan. Its value is the capacity to continuously replan. A static script is like a printed map. The moment a road is closed, the document is useless. The planning agent operates like a modern GPS. When reality blocks the route, it silently recalculates a new path without requiring you to turn around and go home. Agent number 1 relied on heuristics, conditional logic, and a memory bound to a single session. The planning agent replaces those with dynamic revision loops and persistent cross-project learning that spans multiple execution cycles. You cannot achieve system autonomy by trying to perfectly predict every variable in advance. You achieve it by building an architecture designed to catch execution failures and adapt to them in real time. This diagram shows the complete anatomy of the planning agent core. Notice that the arrows do not form a linear pipeline. They form a continuous 6-stage cognitive loop. Stage 1 is goal intake. The system receives a high-level, abstract objective from the user or the orchestrator. In Stage 2, Decompose, the agent translates that goal into a directed acyclic graph, or DAG. It breaks the objective down into a hierarchical tree, calculating which subtasks must run sequentially and which can execute in parallel. With the tree established, Stage 3 is Orchestrate. The agent acts as the system conductor, pushing individual tasks out to external APIs, specialized tools, and downstream subagents. Stage 4 is the Monitor phase. This execution feedback loop tracks milestones against the initial plan. When an API times out, or a subagent returns a runtime error, this laner catches the failure. That trigger initiates Stage 5, Replan. The agent isolates the exact point of failure and surgically rewrites only the broken subtree. The parallel branches continue their work uninterrupted. Finally, Stage 6 is Memory. The agent stores the successful recovery path and the completed task data, persisting that knowledge for cross-project learning in the future. This specific, closed feedback loop is the mechanical difference between a language model generating text and a resilient, production-grade system managing an entire project. Looking at a 6-stage flowchart gives us the theoretical shape of the architecture, but mapping the logic is only half the job. To validate this design, you have to watch the DAG decompose a complex objective, encounter a hard failure, and autonomously rewrite its own plan inside an active terminal. The theoretical breakdown is complete. We are going to take this exact architecture and build it in real code. That's the architecture on paper, 6 stages, 1 loop. To see it actually hold a goal together, decompose, fail, and replan in real code. Now, let's watch it run.
The screen is the atomic unit of a planning agent, the task data class.
The Python implementation defines parameters for a single piece of work. Crucially, the dependencies field declares which tasks must finish before others begin, establishing a networked execution topology. Naive agents execute steps sequentially, a simple to-do list. A true planning agent organizes work into a directed acyclic graph, or DAG, ensuring prerequisite steps unlock downstream actions in a mathematically sound order. Before the agent can execute that graph, it has to build it. When handed a high-level objective, the agent runs a decomposition routine, breaking the main goal down into a structured tree of sub-goals and localized tasks. The underlying decomposition function doesn't work in a vacuum. It queries an internal knowledge base using a command like recalsimilar, drawing on historical project data and prior strategies. Referencing prior runs anchors the language model's reasoning. Instead of inventing an untested workflow from scratch and risking a logic hallucination, the agent adapts proven cross-project learnings to fit current constraints. Structuring the objective mathematically as a DAG creates a rigorous boundary. It separates reactive scripting from strategic planning, providing the precise blueprint required for complex orchestration. Look at this ready function in the orchestration logic. It acts as an execution gate, continuously scanning the dependency arrays to confirm all prerequisites are complete before allowing a task to fire. When multiple tasks have no outstanding dependencies, this gate unlocks them simultaneously, allowing independent branches of the graph to run in parallel. This fan-out pattern optimizes throughput. Frameworks like LLM compiler use this parallel scheduling to achieve up to a 3.6 speedup. Once tasks are executing, the system enters a continuous monitoring loop, evaluating the real-time status of each node against expected outcomes. If a node returns an error, the agent halts that specific branch. Crucially, this failure doesn't force a full restart. The agent evaluates the error and surgically injects a corrective node into the affected branch, allowing overall execution to resume seamlessly once resolved. Once the entire graph resolves successfully, a memory storage function archives the initial goal alongside the final executed plan. Mapping abstract strategy to deterministic graph primitives provides the error recovery and state management needed to deploy these agents in live environments. In high-stakes enterprise environments, this self-healing architecture becomes necessary to prevent catastrophic failure in long-running jobs. Consider an agent orchestrating a zero-downtime database migration. The plan starts with an audit, spins up new instances, then executes a parallel fan-out, copying hundreds of tables simultaneously. Mid-flight, a specific table throws a character encoding error. Malformed data causes a localized crash. The agent's monitoring layer detects the exact node failure. Because the workload is a DAG, surrounding branches are unaffected and continue copying without interruption. The agent processes the failure trace, splices a new cleanup step directly into the graph above the failed node, and retries the operation. A data error at 3 a.m. doesn't trigger a pager alert. The agent analyzes the stack trace, adjusts the procedure, and fixes the issue locally. True autonomy is the capacity to localize and resolve edge cases dynamically without manual intervention. We see the exact same architecture applied to orchestrating multi-channel marketing campaigns. Here is the hierarchical task decomposition for a product launch. A broad mandate is broken down systematically into specific, actionable subtasks. The agent structures the workstreams into parallel tracks. Content creation, ad design, and event booking branch out to run concurrently. Each of these subtasks delegates work to specialized external APIs. The agent coordinates calls to market research platforms, content generators, and calendar scheduling endpoints. Notice the execution feedback loop connecting the active tool calls back to the core engine. This ensures the ongoing results continuously inform and align with the high-level goal. If this were programmed as a static list, a delay in designing banner ads would freeze the entire project. Linear sequencing breaks down under the weight of real-world concurrency. However, sophisticated orchestration is not a universal solution. You have to know when a planning agent is the wrong tool for the job. Do not deploy a planner for tasks with strict latency constraints or single-step actions. Generating a structured plan and managing state across a graph requires compute cycles. For an immediate single-step operation, that coordination overhead introduces an unnecessary delay. Fast tactical responses should be routed to an autonomous decision-making agent, bypassing the planning layer entirely. The second major constraint is the risk of logic hallucination in unverified environments. If the underlying language model hallucinates during the initial decomposition, it can invent false dependencies. It might tell the system to wait for data that doesn't exist, effectively deadlocking the graph. Resolving that specific risk requires advanced verification steps, a capability we will explore later with specialized data and logic agents. A planning agent is not built for raw speed. Its utility comes from enforcing structural dependencies and dynamically self-healing long-running tasks. Let's step back to our map of the 30 foundational architectures. We started with the autonomous decision-making agent, the engine for rapid, single-step execution. Now we've established the planning agent, a strategic orchestrator capable of managing dependency-aware tasks over extended periods. But relying exclusively on these two architectures exposes a vulnerability for long-term AI deployments. The planner is effective at recovering from failures inside an active loop, but the moment the final objective completes and the session closes, the agent suffers amnesia. It cannot carry the nuances of this week's database migration into next week's architecture deployment. The learned lessons vanish. While it can dump execution logs to a file, the core agent lacks the internal machinery to natively query across a timeline of past sessions. To build a system that genuinely learns, you need a persistent, dynamically queryable memory substrate. You need an agent that remembers. That missing layer is the memory-augmented agent, and it completes the foundational cognitive tier. To review the complete code implementations for both the DAG orchestrator and the execution loop, check out 30 agents every AI engineer must build. Links to the book and all associated resources are in the description.